Today we're doing some more Calculus 2 practice problems, focusing on area between curves. So finally we have started applications of integration. We just did all of the heavy integration in the past 7 videos, and now we're doing applications. So if we wanted to find the area between these two curves, I propose that we find the area under one and subtract it from, or subtract the area under the second from it. So the area under the second of some function h of x, right? It's just 0 to x in this case, or between two bounds, the integral of the function. And the first one is just of the first function, so we can subtract those two integrals to get the area in between, and finally, since they have the same bounds, condense it into one integral. So let's do this with this example. These examples are asking us to find the area between curves, right? Pretty straightforward. Between these two curves, y equals x squared minus 6x, and this curve y equals 0, right, we are able to find the area between them. In addition to the formula, right, let's realize why the formula makes sense. If we take some rectangle right here, right, it has some width, super small, delta x. What is the length? The length is just the displacement between the two functions. So if we take this rectangle, right, it has some width, delta x, and the displacement between the two functions would be like that f of x minus h of x then, or in this case 0 minus x squared minus 6x. So let's test to make sure that this slice makes sense. At x equals 0, this slice right here at the origin should have a height or a length of 0 because it's at the very up corner, right? So if we plug in 0 into our display or our length function here, we have 0 minus 0 minus 0, right? So that equals 0. We know that it's correct. Let's just test somewhere in the middle. Let's see how long is it in the middle. So right in the middle between 0 and 6 at 3. Let's see, we have 0 minus 9 minus 18, right? And this becomes positive 9. Okay, so that means that the slice in the middle is 9 long, this slice right here. It's 9 long and delta x wide, right? So this makes sense. What we can also do is approximate the area before we do the integral. We know that if we were to make a rectangle just like this, right, it would have a height of 9 because in the middle of this shape, it's obviously the longest, and we just proved that that length was 9. And at the top, it's 6 wide. So the area of this rectangle that I just outlined is 54. And obviously we're missing out of it. So we know it's going to be less than 54. I'm going to take a guess that it's maybe 40, 38 to 40, right? We took out all of this area from 54. I'm going to guess 40. Okay, so now let's actually do the calculus. If we take one slice, right? One slice or one rectangle has this area, negative x squared minus 6x times delta x. This is the length, this is the width, this is the area of one slice, right? And I want to add up all of the slices going from 0 to 6 with n amount of rectangles. And I want a very accurate number, right? So I want to also take the limit as the number of those rectangles approaches infinity. After infinity amount of rectangles, you can see it would almost look like this, very thin rectangles, and we actually get the actual area, right? And do you remember back from Calculus 1 with the Riemann sums, what this turns into? This just turns into an integral. And we can take that negative out, x squared minus 6x. And that delta x from the summation will turn to a dx. dx just represents a differential amount of x, or a very small amount of x. And of course we're going from 0 to 6, right? So this part right here just turns to the integral. So let's evaluate the integral. We have negative, when you integrate x squared, you get x cubed divided by that new number. And when you integrate 6x, you're just going to get 3x squared. Now at this point in Calculus 2, you may be allowed to use a graphing calculator to solve integrals. On most graphing calculators that I've seen, it's called fnint. You can find it by clicking the math button. And at this point in calculus, if you got through that first test all right with all of the hard, heavy integrations we did, they don't really care about the integration part. They care a lot more that you get to this point than getting the correct answer. But obviously, getting the correct answer is important as well. But this one we can just do by hand. 1/3 6 cubed minus 3 times 6 squared. And when we plug in 0, we're going to get nothing. And let's see, I'm going to plug this into my calculator to get that inside turns into negative 36. Negative 36 is just 36. So the area is 36, right? So what was my guess? 40, right? So we know, obviously, if the answer we got from this integral was like 500 or something, we know we messed up. It's definitely good to take a minute to approximate. So let's look at another question. What is the area between these two curves? We run into a different problem now. This slice right here is represented by the displacement between this function and this function. But this slice right here is represented by the displacement of, again, this function and this function. So it's two different displacements, which means their length functions are different. So that just means that we have to have two integrals. We can find the integral of -1 to 0. That is going to represent all of this integral, right? And what is the displacement? Well, it's the top function minus the bottom function. This is the top function, so 3x cubed minus x dx, right? This represents the area of one slice, and this integral right here represents adding up an infinity amount of those slices, right? And then we want to add that, we're going to add it to the integral from 0 to 1 of this infinite amount of slices, which is instead 0 minus 3x cubed minus x. This is the top function minus the bottom function. Top minus bottom gives displacement, as does right minus left, which we will look at later. So we can add up these two integrals, and we're going to get, once we plug in everything, well, let's see. We can pull the 3 out, integrate x cubed, you get 1/4 x to the 4. Integrate negative x, you get -1/2 x squared. We're going to evaluate that at 0 and -1. So, also we could do this one. It's going to be -3 1/4 x to the 4 minus 1/2 x squared, right? And we're evaluating that one at 1 and 0. But do you see that these regions have the same exact area, right? They are symmetric. So we could just find the area of 1 and double it, right? So which one looks a bit easier to solve for? I'm going to say this one. I like to plug in the positive number first. So this one, I'm just going to double it 2 times -3 times, let's actually plug in the 1 and 0 now to get 1/4 minus 1/2 minus, and then when you plug in the zeros, you just get 0, right? So now we have -6 out of 1/4 minus 1/2. That's just equal to -6. 1/4 minus 2/4 is -1/4. And -6 over -1/4 is just 1.5, right? So what would have happened is this would have given you 0.75, and this integral would have given you 0.75. But since they are symmetric, symmetric, we could just double one of them and save ourselves some work. The point of this question, though, is that we do need two integrals because we have two different kinds of slices, two different regions. In summary, this region is this function over this function, but this region is this one over this one. So we have to account for that with two integrals to just get 1.5. So in physics, we care about a few things. We care about significant figures, we care about units, we care about exact answers, or I mean approximate answers. In calculus, we don't really care about units, and we don't really care about approximate answers. So for example, if you get some area just being pi, right, you could just leave it like that in calculus, because that would be an exact answer. The exact answer is 3.14 dot 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 dot, right? But in physics, you're not going to say that you went and ran like pi miles, right? That doesn't make sense. You'd say that you went and ran 3.1 or 3.14 miles. So we're always just going to leave the answer as exactly what we get it. Like you can leave it as a fraction or a decimal. I chose to change this one to a decimal, but for example, if we were to get pi, we could leave it as pi, and we don't have to include the units. Okay, now they're asking us to sketch the region bounded by the graphs of the two equations and then find the area between them. So at this point, you could probably use a graphing calculator to do it. The only part of doing it with or without a graphing calculator is finding what to integrate from into. In this case, they already took care of it. They told us that we're going from 0 to 1. And once I graph it, it'll make more sense. So x squared minus 1, it has a y-intercept of 1, and then it's going to grow like an exponential function, kind of like that, right? And then minus x plus 2, it has a y-intercept of 2 and a slope of negative 1, so it's going to go like that. But this x equals 0 and x1 just means we're only concerned about this region right here. This is the only region we're concerned about, right? So if you wanted to find what points do they intersect at, like we'll look at in the next problem, we have to set the two functions equal to each other. And you can do that with some of the functions on your calculator. But it's pretty easy to do by hand. So how are we going to find this area? Well, if we take a slice like this, right? What is the length of that slice? Well, it's just whatever this function is at minus whatever this function is at. That tells us that the displacement between the two functions is this function minus this function, right? So we're going to integrate between 0 and 1. This is area. And the width is delta or dx. The displacement or the length of this slice is the top function, negative x plus 2, minus the bottom function, x squared minus 1. So this gives the length of any arbitrary rectangle between 0 and 1, and this is the width. And we can integrate them to find the total area. So let's see, this really is the integral from 0 to 1 of negative x squared minus x. We have a plus 1 and a plus 3, that makes a plus 3, right? Or a plus 2, a plus 1 and a plus 2, that makes a plus 3 dx. So at this point, you can either solve the integral with your calculator or do it by hand if your professor doesn't allow that. This one won't be too bad to do by hand. Finally, we get negative 1/3 minus 1/2 plus 3. So let's find some common denominators. 6, right? We have negative 2/6 minus 3/6 plus 18/6. That leaves us with 13/6. And like I was saying earlier, we could just leave it like that because that is an exact answer. And if that was a decimal, it would be a repeating decimal. But at least in physics, they would rather you approximate that repeating decimal than leave it as a fraction. But that gives the area between these two curves from 0 to 1. Okay, so now let's look at one where they don't give us any bounds for x. So we're going to have to figure those ones out ourselves. Let's graph x to the 5th plus 2. You might say that you don't know how to graph x to the 5th plus 2, but it's really just going to track like x cubed. It's going to go kind of like how x cubed does. The only difference is it's a bit like flatter right here because numbers closer to 0 are smaller. But x plus 2 is simple enough to integrate. it's just like this. It's a line. So the area between the curves is obviously all of this area and all of this area. So we're definitely going to need two different integrals, right? Where does one start, though? Let's see. Where do these integrals start and finish? We have to figure out the x values where these two functions equal each other, because you agree that at this point, and this point, both these functions have the same x value. So let's set x to the fifth plus 2 equal to x plus 2. We know that 0 is a solution because that's both of their y-intercepts. If we subtract 2 from both sides, we have x to the fifth equals x. And before doing any more algebra, let's just think what values of x, what realistic values of x are they going to equal each other? Well, we know 0 is 1. How about 1? Is 1 to the fifth power the same as 1? Yes. And sometimes it gets tricky with the negative 1, because if it's an even power, that negative 1 is going to turn to a positive 1. But since this is an odd 5 power, negative 1 to the fifth power equals negative 1. So that tells me that the x value here is negative 1. This is obviously x equals 0. This is x equals 1. So we have to find the bounds by setting them equal to each other or tracing them in your calculator. Okay, so what is the area? Well, we have two different slices as well, right? This slice right here is given by this top function minus this bottom function. And the top function is the x to the fifth plus 2. The bottom function is x plus 2. But this slice right here, the displacement is the x plus 2 on top and the x to the fifth plus 2 on the bottom. So we could write this as two integrals. The integral from negative 1, not negative 0, negative 1 to 0 of the displacement of the functions x to the fifth plus 2 minus x plus 2 dx. And then we're going to add to that the integral of 0 to 1. And they're going to be flipped. Now we have x plus 2 on top and x to the fifth plus 2 on the bottom. Once again, we run into symmetry, because isn't the area of this whole region right here the same as the area of this whole region? So can't we just find the area of one of them and double it? Yes, we can, right? So we could, let's see. I'm going to choose to evaluate the integral on the right. The integral on the right is going to turn into, and we're just going to have two of them, two integrals from 0 to 1 of, let's see, a negative x to the fifth and an x, right, dx. That's going to turn to negative 1/6 x to the sixth plus 1/2 x squared. We still have that 2 in front. We're evaluating at 1 and 0. 2 negative 1/6 plus 1/2. That would be 2. Negative 1/6 plus 1/2 is just 2/6. 2 times 2/6 is 2/3. So the area between these two curves is 2/3. But you have to intuitively piece together that the area is two different areas. The area of this one from negative 1 to 0 and the area of this one from 0 to 1. So that's how you find the area between two different curves using integral.